The first time I was exposed to university-level mathematics, I felt very overwhelmed by all the theoretical concepts, which at the time were taught to me with almost no visual aids. In fact, I was so frightened that after just one semester of pure mathematics, I quit and switched to engineering. While studying engineering, I learned how mathematics finds applications in the real world, and I fell in love with mathematics again. In this video I want to share with you one application of mathematics that probably fascinates me the most. The surprisingly beautiful mathematics behind how objects deform. There are several good reasons to study the mathematics of deformation. For example, it is essential when you want to simulate the flow of fluids or the deformation of solids using computers. But this is not the main reason why I find this subject fascinating. What I really love about this subject is that humans have a very intuitive understanding of deformation. Think about it, we've been playing with dough or making mud pies since we were kids. From a young age we learn how things bend and stretch. Deformation is something that we can see, and the mathematical concepts behind it can be visualized, which makes them less abstract and way more accessible. To describe deformation mathematically, we need a little bit of calculus, but beyond that we will see that deformation is mostly related to linear algebra. Concepts like matrix vector multiplication, inverse matrices, matrix decompositions, determinants, and eigenvalues and eigenvectors naturally appear when studying the deformation of matter. It almost feels as if linear algebra was specifically invented to describe deformation. So when studying deformation, you will see that all these abstract mathematical concepts can have a very physical or geometric interpretation. Maybe you know already that matrix vector multiplications can be interpreted as linear transformations of vectors. If we multiply a given matrix F with a vector capital X, we get the transformed vector lowercase x. We can illustrate this transformation for any arbitrary input vector capital X. But as we will see later, a matrix vector multiplication alone doesn't tell the whole story of deformation. A matrix vector multiplication is a linear transformation, meaning that it can only describe relatively simple deformations. In reality, we typically see more complex deformations. In this video I would like to show you how we can still use some fairly basic mathematical concepts to describe these more realistic deformations. Specifically, as we will discuss later, instead of just one matrix vector multiplication, we need to consider infinitely many of them, one for each point in space and every moment in time. Before we dive into the mathematics, let me give you some brief historical context. The mathematical study of deformation has its roots in mechanics. Since Isaac Newton laid the foundation for classical mechanics, humans have been searching for mathematical laws that explain the motion of objects through space and time. But soon researchers began to ask more than just how objects move. They wanted to understand how objects and the matter they are made of deform. This curiosity led to what is now called continuum mechanics. In continuum mechanics we distinguish between two theories for describing deformation. A simplified linear theory which assumes very small deformations, and another more general nonlinear theory for describing large deformations. In this video we will focus on the more sophisticated and arguably more interesting theory for large deformations. So let's get into it. Let's consider a three-dimensional volume that is filled by some matter. It could, for example, be a drop of water or a rubber ball. It really doesn't matter. It's funny, German professors like to call this the continuum potato, although my Italian professor preferred to call it the continuum mozzarella. Let's introduce a coordinate system defined by the basis vectors e1, e2 and e3. And let's also consider the time t. In this video we will assume that at time t equals 0, our potato is not deformed. This is our starting point, the initial condition. It is also called the undeformed configuration or reference configuration. As time evolves, some forces may act on our potato such that it is deforming. What we see now is called the deformed configuration or current configuration. How the current configuration looks like depends on the value of t. The reference configuration, which I illustrate in gray here, is not changing over time. And at time t equals 0, the reference and current configurations are coinciding. Just a quick disclaimer, in this video we will switch back and forth between 3D and 2D visualizations, because some of the concepts that we will discuss can be better visualized in 2D. But all the equations that we will consider are formulated in 3D. So how can we describe the deformation of our potato mathematically? Let's take a look at one point on the potato, and let's track this point during the deformation. You can think of this as drawing a small dot on the potato before deforming it and then following its motion through space over time. Or you can think of it as tracking the motion of an atom or a small particle in the potato. The point in the undeformed reference configuration is usually denoted by a capital X. It's a vector with three components, x1, x2 and x3. Of course, in this 2D visualization you can only see the first two components. I know it's a bit unusual to use a capital letter for a vector, but it's a convention to use capital letters for undeformed things and lowercase letters for deformed things. So, following this convention, the point in the deformed configuration is denoted by a lowercase x, again a vector with three components. We can also draw more points on the undeformed potato and track their motion in time. Actually, we are interested in the motion of all points on the potato. To describe the motion of all points mathematically, we introduce what is called the deformation mapping or motion mapping. The deformation mapping phi is a function that takes as input the reference point capital X and the time t, and it returns the current position of the point lowercase x. Because lowercase x is a vector, the deformation mapping is a so-called vector-valued function. It can be interpreted as the composition of three scalar-valued functions, one for every component of lowercase x. The deformation mapping looks quite abstract at the first glance, but it really isn't. Maybe it's best described with an example. For the specific deformation shown here, the deformation mapping looks like this. I intentionally chose a complex deformation mapping to get an interesting looking deformation. But we can also consider a simpler example. We can be very creative on how to design the deformation mapping. For example, here's one that includes a sine wave. Let's go back to the original example of the deformation mapping. There are different ways you can interpret the deformation mapping. For example, you can set the time t to a specific value. In that case, the deformation mapping gives you the deformed points lowercase x at this specific moment in time, dependent on the reference points capital X. For t equals 0, the deformed points equal the undeformed points, and as we increase t, we get different deformed configurations. But there's also an alternative way to think of the deformation mapping, which is better visualized using the sinusoidal example. You can insert any specific choice for capital X, and the deformation mapping gives you the deformed point lowercase x as a function of time. For example, let's insert the point capital X equals 1, 2, 0. The deformation mapping gives us the path that the point is following during the deformation. And for each point that we insert into the deformation mapping, we get a different path. By the way, in the examples that I've shown so far, the undeformed configuration was a circle or a sphere. But we can also consider other shapes and observe how they deform considering different deformation mappings. And we can also visualize the deformation in 3D. And as a side note, in the previous examples I've assumed that the first two components of the deformation mapping, phi1 and phi2, do not depend on capital X3. And I've assumed that the component lowercase x3 equals capital X3. This means that there is no deformation in the x3 direction. In continuum mechanics, this is called plane strain. I will assume plane strain for all examples that we discuss in this video, because it is easier to visualize. But the equations that we will discuss also hold for more general out-of-plane deformations. Okay, I hope that by now you could develop some intuition about what the deformation mapping is doing. It's simply a function that takes an undeformed point and a time as input and returns the deformed point. If you have any questions, don't hesitate to ask in the comments. Now let's hold on for a second. At the beginning of the video I said that deformation is related to linear algebra. So you might be wondering why we've been talking about everything but linear algebra until now. That's because we had to introduce the deformation mapping first, but we are getting to the linear algebra part in a minute. Specifically in this video I want to show you how rather abstract concepts from linear algebra, like for example the determinant, turn out to have a very elegant geometric and physical interpretation. Back in high school and the first years at university, I just learned the rule for computing the determinant by heart, without understanding its meaning and why it matters in physics and engineering. Studying the deformation of objects clarifies in a very visual way what the determinant and other concepts from linear algebra mean and why they are useful. Of course, the deformation of objects is not the only area where linear algebra is applied, but I believe that it is the most intuitive and visualizable one. Okay, let's see how the linear algebra comes into play. Until now we have only considered how points move during the deformation. Next we will take a look at how points move relative to each other. Let's draw a new point right next to our original point and let's assume that these points are extremely close to each other. As the object deforms, the points change their relative position. Understanding these changes is useful because it reveals how the material is being expanded, compressed or sheared during deformation. In the context of continuum mechanics, this is important for understanding the stresses acting at each point in the object. But stresses are a topic for another video, here we just focus on deformation. Another way to think about the relative movement of the points is to draw a vector from one point to the other and then track this vector during the deformation. You can think of this as drawing a tiny line on the potato in the undeformed configuration and then see how this line deforms during the deformation. You may also think of it as following the deformation of a small fiber within the material or a streak in a flowing liquid. But it's important to emphasize that we assume that these fibers or streaks are extremely small. Small enough that we can focus only on their rotation and elongation while ignoring any bending. We denote the undeformed line element by d capital X and the deformed by d lowercase x. Both are vectors with 3 components. Let's draw some more line elements on the undeformed potato and see how they deform. Does it remind you of something? The deformation of the small line elements looks a little bit like the transformation we get from a matrix vector multiplication, as we have seen in the beginning of the video. In fact, as I will show you now, it turns out that the deformed line element can be computed as a matrix multiplied by an undeformed line element. To understand why this is the case, we need a little bit of multivariate calculus. Specifically, we need the so-called gradient of the deformation mapping, or in short, the deformation gradient. Recall that the deformation mapping gives us the deformed x as a function of the undeformed x for every moment in time. The deformation gradient is defined as a matrix that contains all the partial derivatives of the deformation mapping with respect to the components of capital X. The gradient is defined such that a small change of the deformed x is equal to the gradient times a small change of the undeformed x. This formula is a direct result of how the gradient is defined. Maybe you remember that for a conventional function y equals f of x, a small change in y equals the derivative of f times a small change in x. Using the gradient, we have extended this concept to vector-valued functions, like our deformation mapping. If you're curious and want a deeper explanation of this formula, please leave a comment. For now, just be aware that the formula only holds if the line elements are very small. I use larger vectors here just for illustration purposes. The gradient of the deformation mapping is usually abbreviated as capital F. The deformation gradient is a key concept for understanding deformation. So to build some intuition, we will go through several examples in this video. First, let us compute the deformation gradient of one of the deformation mappings we have considered before. We just have to compute the partial derivatives of all 3 components of the deformation mapping with respect to all components of capital X. The deformation gradient tells us how the line elements deform at each point and every moment in time. We just have to multiply the deformation gradient with the undeformed line elements and we get the deformed line elements. Please note at this point that the deformation gradient contains information on how line elements stretch and rotate, but it doesn't tell us where the line elements end up after the deformation. This information is contained in the deformation mapping, but not in the deformation gradient. When multiplied with the vector of the undeformed line element, the deformation gradient gives us the vector of the deformed line element, but it doesn't tell us the absolute position of this vector. Therefore, we might as well illustrate the deformation of the line elements like this, where, as you can see, the line elements are deforming, but we ignore their movement through space. If we zoom in, you will see now that the transformation of the line elements over time looks even more like the matrix vector multiplication we saw at the very beginning of the video. Before we take a look at some simpler examples of the deformation gradient, this is a perfect moment to hold on for a second and ask why the deformation gradient is slightly different from an ordinary matrix vector multiplication. In an ordinary matrix vector multiplication, the matrix F does not depend on space and time. It gives us for some vectors X the corresponding transformed vectors x. This can actually be interpreted as a very simple time-independent deformation mapping, and the gradient of this deformation mapping is F. If we visualize this deformation mapping for a specific matrix F, we see that the deformation is quite simple. This is because F does not depend on space and time, which means that all line elements are transformed according to the same rule. In continuum mechanics, this is called a homogeneous deformation. In general, however, the deformation gradient changes over space and time, so you can think of this as infinitely many different matrix vector multiplications. Deformations for which the deformation gradient varies in space are called heterogeneous deformations. As you can imagine, in reality deformations are almost always heterogeneous, which means that an ordinary matrix vector multiplication is not sufficient to describe real-world deformations. Okay, to get the better feeling of what the deformation gradient is doing, let's take a look at some examples at a single point. If we consider the deformation gradient at a single point, it is not a function of X, it's just a function of time. Here's an example of F that expands the line elements. Because the deformation gradient only tells us how the line elements deform and not how they translate in space, I keep the origin of the arrows fixed during the deformation. Also note that the chosen size of the undeformed line elements is not important for the illustration. If we scale down the undeformed line elements by a factor, we get deformed line elements that are scaled down by the same factor. But the overall deformation remains unchanged. This is basically what linearity of a matrix vector multiplication means. Here's an example of F that compresses the line elements. This deformation gradient describes simple shearing, and this one describes a biaxial deformation. Finally, this example of F describes a rotation of the line elements. Remember that the line elements are three-dimensional vectors. I'm just showing the first two components of the line elements here. It looks a bit messy, but we can also illustrate the deformation of the line elements in 3D. We started this video by introducing the deformation mapping, which is in general nonlinear. By taking the gradient of the deformation mapping, we linearized the deformation mapping locally to arrive at the linear relationship d_x equals f d_X at each point and every moment in time. What's nice about this is that we can now apply all the theoretical concepts that we learn in linear algebra to the matrix F. And then all of those abstract concepts suddenly make sense physically and geometrically. For example, we can think about what it means to compute the inverse of F. We can also apply matrix decompositions like the polar decomposition and explore what such decompositions mean from the physical perspective. Finally, we can compute eigenvalues and eigenvectors and think about their physical meaning. Unfortunately, we cannot do all of this in this video. But I do want to show you how one specific concept from linear algebra suddenly becomes demystified when we apply it to the deformation gradient. I'm talking about the determinant of a matrix. I remember that as a student I had almost no intuition about what the determinant of a matrix really means, but it turns out that the determinant is actually quite meaningful from a geometric perspective. Specifically, the determinant of f tells us how a small undeformed volume element in the reference configuration changes in volume as it deforms into the current configuration. We write this as d lowercase v equals determinant of f times d capital V. Let's see where this formula comes from. We start off by introducing three specific line elements, which are oriented in the same directions as the basis vectors. Let's denote them as dxa, dxb, and dxc. These line elements can be expressed as a very small number epsilon times the respective basis vectors. Over time, these three vectors transform into the deformed vectors d lowercase x, a, b, and c. The deformed vectors are computed as f times the undeformed vectors, which leads to epsilon times the respective columns of f. Next, we take a look at the volume spanned by the three undeformed vectors and denoted by d capital V. It computes to epsilon cubed. Over time, the volume spanned by the three vectors is deforming, and we denote the deformed volume by d lowercase v. To compute the deformed volume spanned by the three deformed vectors, we use a formula that is known from linear algebra. The volume of a parallelepiped spanned by three vectors equals the first vector cross product the second vector scalar product the third vector. This can be derived from basic geometric arguments. If we substitute the deformed line elements, we get this. And if we now apply the definitions of the cross product and the scalar product, we can show that this is equal to the determinant of f times epsilon cubed, which is equal to the determinant of f times the undeformed volume. So we can see that the formula d lowercase v equals the determinant of f times d capital V is indeed true. Okay, after having derived the formula, let's take a look at some examples to see what this formula actually means. At time t equals 0, the determinant is 1. This makes sense because the undeformed and deformed volumes are equal in the beginning. During the deformation, the determinant changes. For this example, the determinant is greater than 1, which means that the volume is expanding. Maybe this is even better visualized by drawing a circle around the arrow tips of the line elements. In this way, we can see that the volume inside the circle is indeed increasing. Of course, in this 2D illustration, we can only see a slice of the volume, but I hope you get the idea. Let's consider another deformation gradient. For this example, the determinant decreases over time, which means that the volume decreases. There are also deformations for which the shape of the volume changes while the determinant remains unchanged. In practice, we observe such deformations in incompressible matter such as water, certain types of rubber, or certain biological tissues. Okay, we can see that the volume increases if the determinant is greater than 1 and the volume decreases if it is smaller than 1. But what happens if it decreases to 0? Take this deformation gradient as an example. In the beginning of the deformation, the volume is compressed, but after some time the determinant gets 0. This means that the deformed volume is 0. Our three-dimensional line elements have been projected onto a lower dimensional space, which is reflected in our illustration by the circle collapsing into a line. Mathematically, this is not a problem, but physically it doesn't make sense. We cannot compress a potato until its volume is 0. This means that the determinant must not be equal to 0 to get a physically meaningful deformation. From the perspective of linear algebra, the determinant of a matrix being 0 has also another implication. It means that a matrix cannot be inverted. This is because two distinct undeformed line elements can be transformed into the same deformed line element, which means that after the deformation we cannot tell anymore to which undeformed line element the deformed line elements belong to. Physically, this would mean that the deformation cannot be reversed, but in reality, after deforming an object, it is in principle possible to deform it back to its original shape. If we continue with the same example and let time evolve further, we can see that the determinant becomes negative. Physically, this would mean that the potato is somehow penetrating itself, resulting in a negative deformed volume, which makes no sense. Therefore, the determinant of the deformation gradient must be strictly greater than 0 in continuum mechanics. Until now we have only considered the determinant at a single point x, but the deformation gradient actually varies across space, and so does the determinant. The determinant tells us how the volume is increasing or decreasing at each point and every moment in time. Take a look at this example where I illustrate several points during the deformation. I mark the points in blue if the determinant is positive and in orange if it is negative. We can observe that the determinant is negative at the points where the matter penetrates itself. Maybe it's just me, but isn't this fascinating? The determinant, a seemingly abstract mathematical concept, acts as an indicator highlighting the points where deformation is meaningful and where it is not. I find such applications of mathematics extremely intriguing because what appears to be just an algebraic operation on a matrix turns out to have a practically useful interpretation that can be visualized. Maybe in another video we can explore other concepts from linear algebra and see how they can be interpreted in the context of deformation. By watching this video, I hope you have developed some feeling for the deformation mapping and the deformation gradient. At the end I have a little exercise for you. Consider an example in 1D, where the capital and lowercase x are scalars. Be creative and construct the deformation mapping yourself and apply the concepts that we have discussed in this video. It's always a good idea to look at things in 1D. I promise it will clear up any confusion you might still have. If you have any questions, comment below. And with that, we almost reached the end of the video. The only thing that is left to answer is what comes next. Now that we have learned about the deformation mapping and the deformation gradient, what can we do with this knowledge? It's important to note that in this video we have assumed that the deformation mapping is known. In reality, however, the deformation mapping is usually not given. More often we face situations where we know the forces acting on an object and our objective is to compute its deformation. To do this, we typically rely on computer simulations, and to implement these simulations, we need to further develop our continuum mechanics theory. Specifically in this video we are focused on the mathematical description of deformation, but we haven't talked about what is causing the deformation. Focusing just on deformation without caring about its cause is called kinematics. To develop a comprehensive continuum mechanics theory, we also have to define measures of stresses that are acting inside our potato. And we have to introduce material models which describe the relationship between the stresses and the deformation of matter. But all these are topics we will dive into in another video. Until then, stay curious, bye!